All right, welcome to part one of our lecture video series from Monday, May 1st, where we are starting with the warm-up for Hess's Law. So I know this looks like a lot for now, so bear with me. Let's just read kind of this first half and then we'll go on to the second half. So this problem says that the reaction between elemental potassium, elemental chlorine, and elemental oxygen to form potassium chlorate is not directly observable, and that is true. In order for us to form KClO3, we have to go through a bunch of different kind of indirect means in order to see this solid be formed in the lab. So its direct formation from its elemental constituents is actually not something that we can witness. However, that doesn't mean that we're not interested in what's going on with this reaction thermodynamically or thermochemically. So even though we can write out what this reaction is, and we can't measure its heat of reaction, how could we maybe possibly find the heat of reaction if we can't determine its temperature changes from calorimetry, and we also can't measure its standard heat of formation because this is the formation reaction that's unobservable? Well, the only means that we have left for us, if we can't use calorimetry and we can't use our standard heats of formation to determine the heat of reaction, is by applying Hess's law. So I have given us a bunch of different reactions here, and these are reactions who have been observed in the lab and whose heats of reaction or enthalpy of reactions are known. So we know how much heat has been released upon each of these reactions per mole of product formed. These all look like exothermic reactions here. So given this information about reactions that are known, let's determine the heat of reaction for the formation of potassium chlorate from its constituent elements, aka the reaction that is not able to be observed. So again, this is kind of the magic of Hess's law. We could, of course, apply it to observable reactions. It's not just limited to ones that aren't observed. It's just particularly useful for reactions that cannot directly be measured in the lab. So this means that our goal here is to generate this reaction from these reaction building blocks. So I need to think about how I can manipulate these reactions so that I can ultimately wind up with something that sums up or adds up to give me this reaction of interest here. So I'm going to go ahead and label these given reactions A, B, and C. And let's start by looking at kind of some requirements for what is needed on the reactant side of my goal reaction, and then maybe identifying those kind of conditions in some of my given reactions. So let's see here. Let's start with this solid potassium. So my goal reaction requires 1 mole of potassium solid on the reactant side. So if I'm going to go and look for potassium solid, here's KClO3, no, magnesium, KCl, no, here we go. Reaction B has solid potassium, and in fact, this has 1 mole of solid potassium on the right side of the equation, meaning it is on the left side. It's on the side we want, right? It's a reactant. So it looks like if I leave B alone, I might get what I want. Let's take a little closer look at B then. Let's see if we should indeed leave it alone. So B also has 1/2 mole of chlorine gas on the reactant side. And if I look at my reaction of interest, the reaction I'm trying to craft from these given reactions, I see that this also has 1/2 mole of chlorine on the reactant side. So it looks like if I leave reaction B as is, then I'll at least have taken care of 2 of my reactants that are needed. So now let's look at reaction B a little bit closer, because I spy in reaction B something that does not show up in my net reaction of interest. So KCl solid. So reaction B has KCl solid on the product side, and it has 1 mole of KCl on the product side. So this means that I need to manipulate some reaction such that S dot T such that KCl solid, 1 mole of it, is on the reactant side. So I need to find a reaction that has potassium chloride solid, and then I need to make sure that I have 1 mole of potassium chloride solid, not on the product side, but on the reactant side. Because again, I'm trying to flip or multiply or divide each of these reactions in a way that is suitable so that I can get the reaction that I want. And since my reaction that I want doesn't have KCl, I need to get rid of this 1 mole of KCl on the product side. So let's look for KCl in our other given reactions. Don't see any potassium chloride in reaction C, so it looks like reaction A is going to be what we're going to need to manipulate in order to get our potassium chloride canceled out. So let's go ahead and flip reaction A, because this will put 1 mole of KCl on the reactant side. So if I flip reaction A, that means its products are now reactants. So I'll have KCl solid coming together with 3 magnesium oxides to form KClO3 solid and 3 magnesium solid. All right, so if we're keeping reaction B as is, if I were to flip this reaction, then it looks like I will at some point be able to cancel out my KCl. And since I had to flip this reaction here, I need to change the sign. All right, so if I have flipped this, then the heat of reaction is going to be positive 1852 kilojoules per mole. All right, so I'm actually going to now just kind of rewrite reaction B and our flipped reaction A just to see how we're doing in our quest to build our reaction of interest. So reaction B, that was 1 mole of potassium reacting with half a mole of chlorine gas to form KCl solid. And then the flip of reaction A, so I'm just putting a negative sign to indicate that we reversed it, is our KCl solid plus 3 MgO solid going to KClO3 and 3 magnesium solid. So if I were to look at the heat of reaction for reaction B, which I left alone, and then the flipped heat of reaction for reaction A, if I were to add these together, let's kind of see what I would be left with. So I definitely get those KCl's canceled, which is good. That's what I wanted. So this would leave me with K solid plus 1/2 Cl gas plus 3 MgO S going to KClO3 solid and 3 magnesium solid. And so far then, the heat of reaction for this particular reaction, so that's the sum of B and the flip of A, that would be this guy here, 1852, and then minus 437. Let's go ahead and figure that out right now. I get 1,415, and it's going to be positive because of this sign flip here in my heat of reaction of A. All right, So this is what I've got so far, right? I'm starting to get the pieces of what I want. I've got my potassium and I've got my half a mole of chlorine. And let's kind of go back to what's shown up here on my reaction of interest. So it looks like I've got this KClO3 and I have 1 mole on my product side. And wouldn't you know it, so far I have KClO3, 1 mole on my product side. So my mole quantities are good here, which means that I need to find a way to get rid of these magnesium substances. So I've got my magnesium oxide and my magnesium, and I need to be left with now this 3/2 oxygen gas. So let's look over at reaction C. So we need to use what we know about reaction C to hopefully cancel out some stuff that we see in the result of A and the flip of B. So looking at the results of A and the flip of B, I've got 3 magnesiums on the product side, whereas reaction C has 1 magnesium on the reactant side. So I have the magnesium in reaction C on the place of the reaction arrow that I want it to be, right? It's on the reactant side, but I don't have the quantity of moles that I need, which is 3 here. Let's look also at what else we have. We have magnesium oxide on the reactant side in our reaction that we're using to try to build our reaction of interest. And reaction C has magnesium oxide on the product side. So again, the placement of these substances is good. So reaction C has 1 mole of magnesium on the reactant side and 1 mole of magnesium oxide on the product side. However, if we're looking at our reaction of interest, right, we're trying to cancel out 3 moles of magnesium oxide and 3 moles of magnesium. So I need to triple reaction C so that my mole quantities are all consistent with what I need. So if I'm going to triple reaction C, then I'm going to have 3 magnesiums plus 3/2 oxygens going to 3 MgO, and I cannot forget that since I have tripled this reaction, I need to now triple its heat of reaction. So the heat of reaction is now going to be triple what it once was. We did not flip it, so its sign is going to stay the same. So that is going to be 602 times 3, which gives me 1806. And again, sign's going to stay the same. So negative 1806 kilojoules per mole. And let's look at this with our result from up here. So we now have solid potassium plus 1/2 Cl2 plus 3 MgO goes to KClO3 plus 3 MgS, and we had the heat of this reaction calculated to be 1,415 kilojoules per mole, positive. So if I were then to sum these together, I would find that, let's see here, 3 magnesiums on the reactant side cancels with 3 magnesiums on the product side, and then 3 magnesium oxides on the reactant side cancel with 3 magnesium oxide on the product side. And the only thing that would leave behind then is this 3/2 oxygen. So let's go up and check if that's okay for us to have in our resulting reactions. So going back up to our reaction of interest. Yes, we did want 3/2 of oxygen on the reactant side. So we should be good to go. Let's see if that's true when we do our kind of final summation. So this leaves behind solid potassium plus, let's see here, 1/2 Cl2 plus 3/2 O2 going to KClO3. I've got my 1 mole of potassium I have my half a mole of chlorine gas. I've got my 3/2 moles of oxygen gas, and I've also got my 1 mole of KClO3 solid. So that means then that I need to take the sum of these two heats of reactions to get my final overall heat of reaction for the reaction that I care about. So that is 1405 minus 1806. This gives me negative 401 kilojoules per mole. So since this is our reaction of interest that we were able to obtain by manipulating some known reactions and their heats of reaction, we could then get the heat of reaction for this reaction that's not directly observable. So the things with Hess's law, I think that students get most tripped up on is they tend not to write things down, so you lose track of substances. They also tend to drop a positive or negative sign or forget to flip or multiply through some number. So make sure that whatever you do to your reactions that are your kind of Legos or building blocks, you also do it in turn to your heats of reactions. So let's see here, we had to multiply by 3 here. All right, so that is Hess's law. We've now been through all of our different means of determining the heat of reaction, be it through calorimetry using our heat transfer, meaning our Q equals mc delta T, and stoichiometry calculations. We have looked at using the standard enthalpies of formation to determine the heat of reaction, and now we've looked at Hess's law. So that is going to be our wrap up of thermochemistry. We'll still see these thermodynamic things pop up in the future, but they're not going to go away, especially in Chem 220, but we'll still see these again when we look at phase changes. So for now, if we're going to start talking about phase changes, let's start talking about properties of the different phases, which we know is solid, liquid, gas, and we're going to start up with looking at gases. So let's begin our conversation of gases by talking about pressure.